All right, so exam 1 is on Friday. Today, we're just going to do interpolation and do some examples of using interpolation with the property tables. And then the topics on the exam will go up through interpolation. So nothing we do on Wednesday that's new is going to be on the test, but the stuff from today is. Anyone have any questions about the test? It's just going to be problems like the assigned problems. Okay, so to get ready for the exam, as much as you can, go back to the beginning of the assigned problems and just one by one ask yourself, like, do I know the steps for doing this stuff, And when you're pretty, you remember pretty certainly like how to go through that problem, probably skip that one. Go on until you find the ones that you're a little hazy on. Work through those, remind yourself about the steps. You can do the same thing with example problems from class. That's also useful. So I think that's the best way to get ready for it. There won't be any of the like quiz type questions on it. Okay, so linear interpolation.
Hello, Professor.
Hi.
You didn't get my email, or sorry.
I don't
I
know.
also tried the instant message thing to contact you, but
Okay, over the weekend?
basically today morning.
Oh, I don't know. No, I guess I didn't. Okay, so linear interpolation. This is something that's used in all numerical analysis. It's used with tables to come up with values that you want rather than the values that are given in the table. So we're not going to have to use this in this class because, so really, there's that thing. I gave it to you last time. So remember, rather than using this in thermodynamics problems, you can just use IRC dot wisconsin.edu slash properties. And it'll give you the exact values that you'd be approximating by using numerical, linear interpolation. But I am going to require you to, get used to this idea a little bit. I'll give you some simple problems on it on the tests. Okay, so remember, well, let's say for simple compressible substances, which is everything in this class, if you're at saturation, you can think of any property you want So let's call that the property you want, say, is f, as a function of any other one property. Okay, so you can think of the property you want as a function of x, where this x is this other one property. Okay. When you're not at saturation, you can think of any property you want call that f again, as a function of any other two properties. We can think of those as like x and y. And so what that means is when you're not at saturation, the property that you want, whatever it is, you can think of as a function of two other properties. Okay, so linear interpolation works like this. If you have a function f of x plotted versus x, so let's say there's your function. Okay, let me stretch this out a little. And let's say that you want to, let's say you want to know the value of f at x, okay? So you want f at x. But let's say that instead what you know is f at x1 and f at x2. They don't have to be evenly spaced. Okay, so what you know is the value of f there and the value of f there. Okay, you'd like to know the height at x. But instead you just know f at x1 and f at x2. So how would you approximate that value? You can draw a line between these two. That's the linear in linear interpolation. Okay, and then you can approximate the height at x by this. Okay, that's your approximate value of f of x. So that's the idea, and really, if I gave you a little time, you could figure out a way to do that. You know, I'll give you a formula, but you really don't even need a formula. But it works like this. So basically, what's the height of that green point? Well, it's going to be the height of the function at x1, okay, plus this distance times the slope of that red line, right? So we're going to say f of x is approximately equal to f at x1 plus f of x2 minus f of x1 divided by x2 minus x1 times the x that you want minus x1. So this thing here is the rise over run.
GPS signal lost.
Oh no, where are we? So this is the rise over run of the line. And this is like, you can think of that as the delta x. So let's do it for a mathematical function, and then we'll go and do it for some properties at saturation. And I'll give you this formula on tests. So let's say we want to approximate f of x is equal to x squared at x equals 2, okay? Given that f at 1.5 is equal to 2.25 and f at 2.5 is equal to 6.25. Okay. So if this were a thing out of property tables, we wouldn't know what the underlying function was, right? I mean, like, obviously, if you know the underlying function, it doesn't make any sense to approximate it. Just plug 2 into the function and you have it. But this gives us a way to, after we're done, check how close this approximation was. Are you with me on that? And so really, if this was property stuff, it would be like, okay, say we want to find the specific internal energy, okay, and we're given the temperature, okay? Then X is the temperature, F is the specific internal energy. We're given the specific internal energy at 2 temperatures that surround our value, okay? And we're going to use that to approximate the specific internal energy at our value. So f at x equals 2 is approximately equal to f at 1.5 plus f at 2.5 minus f at 1.5 divided by 2.5 minus 1.5 times 2 minus 1.5. And so f at 2 is approximately equal to, now we can plug these values in that we're given. So f at 1.5 is 2.25 plus 6.25 minus 2.25 divided by 2.5 minus 1.5 times 2 minus 1.5. So that is 2.25 plus 4 divided by 1 is 4 times 0.5. And so f at x equals 2 is equal to 4.25. since in this case we knew the underlying function. Okay, let me just write this down and then. So in this case, since we knew the underlying function, we know that the true value that we're trying to approximate is 4. So even though we were pretty far from it on both sides, in this case, we were in the right ballpark. We were better than either of the two endpoint values. Yeah, question? Okay. All right, well, let's do this for a saturation problem. So why saturation? Remember that if we're not at saturation, this is a two-dimensional, like there's two variables that we have to do this for, and I'll talk about how to do that next. You basically go in one direction and then you go in the other direction. Okay. So now let's do an example, and I'll get some values out of D2L in only 46 short clicks. Okay, so let's do it for water at saturation. So I'm going to go to tables. Let's do it by temperature. And so this is the temperature in Celsius. Let's say that we want to consider water that's at saturation at 61.2 degrees Celsius. Okay. So first of all, you're used to the saturation temperature of water being 100 degrees Celsius. What would have to happen for the saturation temperature, the boiling temperature of water, to be 61.2 degrees Celsius, to be a lower temperature? What would physically have to happen? Decrease the pressure. And it makes sense if you think about, remember that that boiling is, so imagine that a substance is just a bunch of rubber balls bouncing around, and higher temperature means they bounce faster, and boiling is those rubber balls escaping from the mixture. Okay, so what would you have to do so that at a certain speed these rubber balls could escape from their mixture? What would have to happen is that there's less pressure pushing down, holding them into this mixture. Actually, this is kind of interesting. Mountain climbers, when they're climbing really tall mountains, Mount Everest and stuff like that, the air pressure is really low. And so they're burning tons of calories, and eating is super important. But it's hard to eat food way up high on the mountain because the pressure is so low that, like in this case, you see the boiling temperature of water is only 60 degrees Celsius. So you get your water up to boiling, and it still is only 60 degrees, and it can't cook the food, So it takes forever to make whatever, oatmeal or whatever you're trying to make, pasta, rice.
And on the opposite side, if you were in find those really high pressure, you could get the water to get higher in temperature than it would be.
Yes, that's right. Yep, that's right.
That's the concept of pressure.
That's exactly right. Yep, exactly.
So instead of taking a long time to cook something at a lower temperature, it takes a smaller time because the temperature is higher and it just gets
correct.
Faster.
Yep, that's exactly right. Okay, so we're going to go at 61.2 degrees Celsius, but we're not given that. And let's say that we want to calculate the specific uh, internal energy for a saturated vapor. Okay, so remember that at that boiling temperature, you can have saturated liquid or you can have saturated vapor. Okay, or you can have a mixture of the two, all at that same temperature and pressure. Okay, so let's go for this example. We want to approximate the specific internal energy for saturated water vapor at 61.2 degrees Celsius. And what we're given in the table is that at 60 degrees Celsius, this is in kilojoules per kilogram. So if I'm going to go in SI units, we're at 2456.6 times 10 to the third. (2456.6), I think it was, times 10 to the third joules per kilogram. And at, what was the next one? We need to go to the other side of the value we want. So 65, it's at 2463.1. Okay. So the specific internal energy at 61.2 is going to be about U at 60 plus U at 65 minus U at 60 divided by 65 minus 60 times 61.2 minus 60. So that's 2456 times 10 to the 6. No, 0.6 times 10 to the third plus 2463.1 times 10 to the third. I could have done this all without the 10 to the thirds, but minus 2456.6 times 10 to the third divided by 65 minus 60 times 61.2 minus 60. So this time what we're talking about is the function is a surface determined by its location above a plane. All right, so let's say that this is the surface. Okay. And this surface lives above the XY plane. And if we extend, let's extend some of these. Oh, and it's a grid, so that's important. There's 2 dimensions of independent variables. And so the value of the function would be like here, and that would be determined by where it is above a grid point like that. Okay. And this would be like, so let me continue these lines out here. So let's say that the location is like that. Whoop, I sort of missed. Okay. And what we would have here is this would be like our x1, our x2, and the red would be the x that we're trying to find. Over here, this would be like our y1, this would be our y2, and this would be like the y we're trying to find. Okay. And if you're looking straight down from above, here's the grid. So here's x1, x2, y1, y2, and the point we want is, let's say, straight above this point. It's that surface where you hit that surface coming vertically up from that point. And this would be our x, and this would be our y. Okay? So to do this, to approximate a function f of x and y, you have to start this time with 4 known values. So this would be the function value. That's the property you're trying to find at independent variable values x1, and I'm gonna put it in a grid. So let me start with this one. So we're gonna have f of x1, y1 here. The one above would be f of x1, y2. The one over here would be f of x2, y1. And the one over here would be f of x2, y2. And then we do 3 applications of that linear interpolation. Of that linear interpolation equation. So the first one would be f at the x we want at y1 is equal to f at x1, y1 plus f at x2, y1 minus f at x1, y1 divided by x2 minus x1 times the x we want minus x1. Okay, so first we keep the y's constant at y1 and do the interpolation on the x's. Then we do the same thing, but we keep the y's constant at y2. So f at x, y2 is approximated by f at x1, y2 plus f at x2, y2 minus f at x1, y2 divided by x2 minus x1 times x minus x1. So the only thing that's different is where we kept y constant in those two. And now we'll do the third one where we approximate f at x, y. So this time we're going to keep our x constant at x, and we're going to do the interpolation over y. So this is equal to f at x, y1 plus f at x, y2 minus f at x, y1 divided by y2 minus y1 times y minus y1. So the first 2 steps of that are getting the values that we're going to then use in step 3. Okay. So let's do this for a mathematical function, and then we'll do it for a table value. So let's say we want to approximate f at, or the function is x squared, y squared. And we want to approximate the value of this function when x is equal to 2 and y is equal to 2. And we're going to do it given the 4 values. So I'm going to put it again in a grid. So f of 1.8, 1.8 is 10.50. F of 1.8, 2.2 is 15.68. F of 2.2, 1.8 is equal to 15.68. And f of 2.2, 2.2 is equal to 23.43. Okay, so step one, we're going to say, so we want to approximate this at x equals 2. So f at 2, 1.8 is approximated by f at 1.8, 1.8 plus f at 2.2, 1.8 minus f of 1.8, 1.8 divided by 2.2 minus 1.8, and then times the quantity 2 minus 1.8. So f at 2, 1.8, if you plug all those values in, you get about 13.09. And now we'll go to the second step. This time we want to approximate the function when x is equal to 2 and y is equal to 2.2. So that is f of 1.8, 2.2, plus f of 2.2, 2.2, minus f of 1.8, 2.2, divided by 2.2 minus 1.8, times 2 minus 1.8. Plug all those in and you get that f at 2, 2.2 is about equal to 19.56. And now we're going to do it with y varying with these two values we just calculated. So now we want to go f at 2, 2, and that's going to be equal to f at 2, 1.8 plus f at 2, 2.2 minus f at 2, 1.8 divided by 2.2 minus 1.8 times 2 minus 1.8. Plug that all in and you get your final approximation is 16.32. Since in this case we know the underlying function, we know that the true value is 16. So we know in this case the true value. Usually, like when you're doing this in tables, you never know the true value, but this gives you a sense of how close it is. One thing I want you to notice is when you're doing this in a table, which property you call X and which property you call Y is irrelevant, you know. Is arbitrary. So, you know, if you're usually your X and Y um, would be temperature and pressure. But in applying these formulas, you could call temperature X and pressure Y, or you could call pressure X and temperature Y. You wouldn't get the exact same answer, but you'd get, you know, equivalent approximations. So X could be temperature and Y could be pressure, or X could be pressure and Y could be temperature. Okay, well, I don't have time to do one out of the table right now, but I'll give you some stuff to do, a couple of problems to do related to that, and let's just stop there.